Welcome and to the Eclipse talk today. I'm going to give you a brief tour of what eclipses are about. Eclipses are due to two motions: the motion of the Earth around the Sun and the motion of the Moon around the Earth. So let's show a couple of slides here. They're a little bit technical looking, but we'll get through them and it'll be fine. So the Earth moves around the Sun over the course of a year. In this schematic here, we see the Earth here and we see June. And if you were to look up in the nighttime sky at midnight in June, you'll see constellations like Scorpio in the sky. On the other hand, if you look towards the Sun, the constellations that are behind the Sun, they don't go away, are lost in the Sun's glare. And so the Sun is in Taurus. You wait a month, the Earth has moved over here. And now you can see constellations like Sagittarius and Capricorn in the sky at midnight, but the constellation of Cancer is blocked off. The plane of the Earth's orbit around the Sun is called the ecliptic. Sound familiar? It sounds like the word eclipse, and that's because eclipses occur on or near the plane of the ecliptic. The other motion that I want to call to your attention is the motion of the Moon around the Earth. So as the Moon goes around the Earth, we want to picture sunlight coming in from the right here. If somebody's standing on the Earth here and the Moon is in this position, then we're seeing the shaded side of the Moon. The illuminated side of the Moon is pointing away from us at the Sun. And because it's near the direction that sunlight is coming from, the Moon is lost in the glare of the Sun and we cannot see it. All right, we call that new moon. But as the Moon moves around the Earth, we can see the Moon in the sky after sunset, and with each passing day, the Moon grows larger and larger in the sky, and it sets later and later. So the Moon appears to go through phases, and after a two-week period roughly, the Moon is on the other side of the Earth from the Sun, and now someone on the Earth sees the illuminated side of the Moon, and we call that full moon. So we would go from new moon, we can't see it because it's lost in the glare of the Sun, to a waxing crescent, then a first quarter, and then after 2 weeks it's full, and then after another week it's third quarter. If you were up early this morning looking up in the sky, you saw roughly a third quarter moon in the sky. And in about another week's time, it will go back to new moon. However, the problem is, looking at this picture, it's deceptive because it looks like if the Moon is here and the sunlight is coming in from the right, shouldn't the Moon's shadow fall on the Earth and we should get an eclipse, a solar eclipse, where the Sun is covered up? And if the Moon is over here, why doesn't the Earth's shadow fall on the Moon and then we get a lunar eclipse? Well, that doesn't happen every month. And the reason for that is that the Moon's orbit around the Earth is tilted with respect to Earth's orbit around the Sun by about 5 degrees. So most of the time, the shadow of the Moon undershoots or overshoots the Earth, so we don't get a solar eclipse. And most of the time, Earth's shadow misses the Moon, and so we don't get a lunar eclipse. Here we are at new moon, here's the Sun, and you can see the Moon's shadow trailing off and missing the Earth. Here's the Earth's shadow, it's trailing off and it's missing the Moon. And that's because the plane of the Moon is tilted relative to the plane of Earth's orbit around the Sun. Now, let's note this blue line here. This is where the plane of the Moon's orbit around the Earth intersects the plane of Earth's orbit around the Sun. As the Earth-Moon system moves to another position relative to the Sun, if that line is aligned with the Sun, and if, so a couple of ifs there, and if the Moon happens to be passing through that point, or the Moon is passing on the other side along that line at that point, then the Moon's shadow can fall on the Earth and we can get a solar eclipse, or the Earth's shadow can fall on the Moon and we can get a lunar eclipse. It's a cycle called the Saros cycle. It takes about 18 years, and even the ancients were able to predict when, not necessarily where, eclipses would be. So quickly, lunar eclipses of the Moon occur more frequently because the Earth's shadow is larger than the moon. The other thing is that if you're on the nighttime side of the Earth, when the Earth's shadow touches the moon, it doesn't matter where you are on the surface of the Earth. So long as you can see the moon in the sky, you can see the Earth's shadow touching the moon. And then you have a lunar eclipse. So over half the people on the planet can see a lunar eclipse. And what does a lunar eclipse look like? It looks something like this. See that beautiful orange bulb? Why do you think it's orange? What you're seeing is light from all of the sunrises and all of the sunsets on Earth. That orange light, filtered light through the Earth's dusty atmosphere, continues on out into space and falls on the moon, illuminating the moon. So if you were an astronaut on the moon during a total lunar eclipse, you would see a big red ring around the Earth, effectively all of the sunrises and sunsets. Here is a series of pictures taken of a lunar eclipse, and you can see that the shadow is about this big. The ancient Greeks knew about this and were able to deduce that the size of the Earth based on the size relative to the moon, based on the size of the shadow. And because every time there was a lunar eclipse, the shadow was round, they were able to deduce that the Earth was round and not flat. Otherwise, you get a little skinny line shadow on occasion. The other kind of eclipse is a solar eclipse, and that's what we're really talking about today. And the thing is that the moon and its shadow are far smaller than the Earth. Only a few people on the surface of the Earth can view a solar eclipse. They're only the people who are in a very narrow band where the moon's shadow falls on the Earth. And so they're comparatively rare for the population on the surface of the Earth. You can't just be anywhere on the sunlit side of the Earth and see a solar eclipse. All right, now there are 3 flavors of solar eclipse. The one that is coming up is called a total eclipse, and that is where the moon's disk completely covers the sun in the sky. The blinding white disk called the photosphere, which you should never look at under any circumstances. Even a casual glance, you can damage your eyes. When the moon completely covers that blinding disk, we say that we have a total solar eclipse. If the moon misses a little bit and only part of the sun's covered up, we call that a partial eclipse. Now, to get to a total eclipse, the moon gradually covers up the sun, and so there is a partial phase of a total eclipse, but sometimes the moon just misses altogether, covering it up altogether, and we call that a partial eclipse. And then there's what we had on October 14th, if you happen to be in San Antonio. That's an annular eclipse where the moon is too far away, appears too small in the sky, and it doesn't completely cover the blinding disk of the sun. Now, what does a solar eclipse look like? It looks like this. It is very spectacular. It is one of the most spectacular natural things that you can view in your lifetime. So if you have a chance, go look at it. This is the last total eclipse in the contiguous United States for 20 plus years. So be prepared to travel abroad if you want to see an eclipse after this coming one. And it'll look something like this in the sky to your naked eye. Prior to the eclipse, you must be wearing safe eye protection during the partial phase. And during totality, during that brief 3-minute period, you take the glasses off, and because the gossamer filaments of the corona are not blindingly bright. If you're on the International Space Station looking down at the Earth, this is what a total solar eclipse looks like. If you're here on the Earth, you would be experiencing a total eclipse of the sun. If you're here, where it's not so dark, you're experiencing a partial eclipse of the sun. Here's another shot. Looks like there's a total eclipse going over Indonesia. The spot's right there. The spot where totality is only about that wide. The shadow of the moon races across the Earth at about 3,000 miles an hour, and people sometimes report getting a sense of vertigo if there's low-lying clouds, and because they can see the shadow coming at them, and people literally duck because it's such a big thing coming at them. Of course, it's just a shadow, but still, psychologically, it affects them. If you don't have a pair of safe solar viewing glasses, you can try pinhole projection. So take a piece of paper, poke a pinhole or a pencil hole in it, and take another piece of paper, and it will make a pinhole camera image of the eclipse. This very clever person has just balled up their fist to make a little hole through their fist, and you can see this crescent shape there. That's the crescent pinhole image of the sun occurring during an eclipse. Here's another clever one. Somebody took a colander, and if you look very closely at the colander, you can see that they're all crescents. These are crescent pinhole images. When I was a graduate student at the University of Kentucky, I was so wrapped up in my graduate studies of astrophysics, I had forgot that there was a partial eclipse of the sun where the sun was going to be covered up almost 98%. And I was looking out my window. I looked up from my quantum mechanics homework. And I looked out the window and I said, gee, the sky is really blue. And then it dawned on me that the sky isn't bluer. It's because my irises are open up because it's getting darker outside. So I said, oh my gosh, the eclipse. And then I went running outside and looking at bright street lights, which were glowingly bright, and the ground where light filtering through tree leaves fell on the ground, making a pattern like this. See all these little crescents there? These are pinhole images of the partial eclipse that is going on. If you do want to look directly at the sun, you need safe solar viewing glasses. And while there are knockoffs, there are some safety guides that you ought to follow. You want to look for ISO 12312-2. Sometimes there's a year here, sometimes there isn't, but that needs to be on your glasses. Otherwise, you don't know whether they're safe or not. There are knockoffs, that forgeries that people make, and and they even put those numbers on them, so it's problematic. But there are safe places to get them. And in fact, I was in the HEB just the other day, and there were stacks of them next to the Easter candy for $1.49 each, and they had the right number on them, and they were from a reputable astronomy instrument company, so I think they're okay. Now, if you go to a viewing event and you're going to look through a telescope, here's some things that you want to check. You want to make sure that there is an objective side filter, a big shiny mirror-like covering on the operating end of the telescope, like this, okay? Walk up to the telescope and the operator, maybe there's a line, maybe there's not, but walk around the front of the instrument first and see if there's a large mirror-like covering. Okay. If there isn't, don't look through the telescope. In the olden days of the 1960s, you would get a solar filter, which is about the size of a quarter, and it would screw into an eyepiece. And the problem with that is that as time has gone by, telescopes have gotten bigger, they collect more light, and those little black glass discs get hot and they can crack. And as soon as they crack, they can let the blinding light of the photosphere through. And in about a millisecond, you'll lose sight in that eye, or you'll have eye damage. So only look through a scope if it's got one of these things in front of it, okay? Here is a partial eclipse going on. Do you see those little dots there? Does anybody know what that is? That's the International Space Station. It's a series. This is a video clip, and this is a series of video frames. And so if you want to know what a 10-story high building looks like at an altitude of 300 miles, next to the sun in the sky, that's what it looks like. Now, I mentioned size and distance are important, so sometimes the Earth is a little bit closer, sometimes it's a little bit farther. The Earth's orbit around the sun is not a perfect circle. It's off by 1% or so. And the moon's orbit is more so, roughly 10% or so off. So if the moon is small when it gets in front of the sun, not all of the sun is covered up, and you get an annular eclipse like this. And here's another beautiful shot of an annular eclipse like we had on October 14. And here's another beautiful shot of an annular eclipse. It even happens on other planets. The Curiosity rover on Mars on 2013 captured the moon Phobos passing in front of the sun, and there's the oblong shape of the asteroid remnant moon Phobos passing in front of the disk of the sun from the planet Mars. I went to the 2017 eclipse of the sun. I was on the Wind River Indian Reservation. Here's my setup. How can you tell it's a scientist? There's a bunch of telescope stuff and an old white Subaru. So that's just a real tip-off. This is what the telescope apparatus looks like from the working end. Here's that shiny mirror thing. For the totality part of the eclipse. So mirror things, even down here, mirror things and everything. For the totality part, this mirror thing flipped open and light comes through the telescope, because during that time you can safely look at the sun. So here's some of my pictures with the moon getting progressively more and more in front of the sun. The little black dots are sunspots. That one right there is maybe 2 or 3 times the size of the Earth for scale. What does an eclipse look like from the ground? Well, the top picture, my friend was in Nebraska. There's a top picture during the daytime. The bottom picture is in the daytime too. But this is during the eclipse. The sky turns a blue-black color. You can see the brighter stars in the sky and bright planets in the sky, and it is orange-red around the entire horizon, 360 degrees, because light from outside the shadow region is filtering in, so it looks like sunrise and sunset in every direction towards the horizon. Here's one of my intermediate exposure pictures of the sun, just taken with an old World War II aerial photography lens that I bought at an auction when I was a kid, 15 years old, and I built a telescope out of it, and it took a perfectly fine photograph. I took a series of photographs, long exposures and short exposures. In the short exposure, you can see eruptive prominences coming off the side of the sun. We're now in a period, unlike 2017, where the sun is really active, so there ought to be a lot of prominence activity going on. And there ought to be a lot of coronal activity going on. So those gossamer white filaments that you see ought to be much stronger than they were in the 2017 event. There's a close-up. And here is a photo composite of my long and short exposure pictures. And that is kind of what you will see naked eye during totality. As soon as totality is over, just the moment you see a flash of light, almost like if you're turning around in a corner in a car and the sun catches you in the eye, put those glasses back on right away. Instant, it gets bright again. Put your glasses back on. Don't tarry, otherwise you'll hurt your eyes. What about the April 8th eclipse? There's a NASA path. There's lots of websites to figure out where you ought to be to have totality. I use a website called Astrospheric. It's a weather website, but there's a little tab that says 2024 eclipse. You click on it, and if you're inside the green band, you will have totality. If you're at the southeast edge of Austin, you may not have totality. Get yourself further west, though it's going to be crazy in the hill countries. Okay. They'll have 4 minutes and 30 seconds-ish of totality in the hill country, but there will be millions of people there. I'm perfectly happy to be here on this campus with only 3 minutes and 30 seconds. It'll be busy enough here. We think maybe 3,000 or 4,000 people will be on campus on that day. Here in Georgetown, Texas, the partial phase, where the moon just starts to cover the sun, begins at 12:18. Totality's around 1:37, and so plus or minus a minute and a half on either side is when totality is. And we'll have about 3 minutes and 15 seconds of totality. Another site I checked, the U.S. Naval Observatory, says 3 minutes, 6 seconds. And so I'd go with the U.S. Naval Observatory any day, but it's a more technical website. So at Southwestern, we're having an event. It's from 11 to 3 that covers the eclipse period. And we have some eclipse glasses, about 1,500 left to hand out. But if you have your own, bring your own. And we'll have 10 telescopes set up on the lawn, the academic mall, to show the partial phases of the eclipse only. It's too unsafe to have hundreds of people in line, take the filter off, have people look and put it back on when everybody's trying to get to the telescope at the same time. So we'll cut it off. Everybody will go back to their picnic blankets or lawn chairs and enjoy the eclipse on the totality part on their own. Trained students will be there to answer questions about the eclipse and keep the telescopes tracking. It ought to be a pretty good experience. It was a great experience for the annular eclipse, and so we just have to multiply by 5. All right, well, thank you very much.